And then we can proceed with the second speaker, which will be Steffen Gielen. And
can you hear me? Yeah, okay.
Yeah, we can. And soon I hope your slides will also appear.
Yes, we have some technical issues.
All right. I hope that's not coming off my talk time.
Yeah, the floor is yours.
Great. So yeah, let me start by thanking the organizers for putting together this really, really inspiring meeting. It's been really great to be here and learning new things. As you can tell, my voice is a bit damaged today, so apologies for that. I hope I can get through this talk okay. So my talk is not so much related to black holes, but has more to do with fundamental questions in quantum gravity, to do with unitarity, what we mean by that, and the consequences we can draw from unitarity, in particular regarding gravitational singularities. The talk will be to some extent related to also the talk that Lucia Menendez-Pidal gave already yesterday, so there will be some repetition, but I will take quite a different perspective here, so I hope it will still be interesting. So these are our papers. We'll mostly focus on this kind of broader perspective taken in this essay that we wrote for the Gravity Research Foundation. So what do we mean by unitarity? Of course, in standard quantum mechanics, this is one of our fundamental principles, which has to do with the probability interpretation of the theory. Our dynamics should be unitary, or the Hamiltonian operator should be self-adjoint. So we would certainly like unitarity to emerge somewhere from whatever our theory of quantum gravity is in the end. So then we have to ask, what do we mean by time evolution, right? So of course t, the coordinate, is just a label, so it doesn't make a lot of sense to use just the coordinate time, but we can advocate this viewpoint that also Bianca already introduced to us on Monday in the very first talk, which is this relational viewpoint, right, which many of us think is kind of the only way of making meaningful statements about evolution. So the clock should really be a matter field, right? So the dynamics of a system should be described relative to, for example, a matter field, which plays the role of time in a certain sense. So then we can ask, if we have such a well-behaved, physically reasonable matter clock, should we require this kind of time evolution to be unitary? There's certainly a clash already here with the general covariance of classical relativity, right? Because, of course, there will be many such clocks in general. And in classical GR, I can always find clocks with unusual properties. And then unitarity with respect to those can lead to strange predictions. And I'll illustrate that in one example, which hopefully makes that clear. So some higher principle seems needed. For me, it's not clear what it is. And in particular, I would argue that by choosing the right clock and going through this, it seems we can always resolve singularities in a particular sense, again, that I will hopefully make clear. So here's the model, which again was already introduced yesterday, but let me review that. So this is our cosmological model here. You have your FRW metric. You've got the lapse function here. You've got your scale factor A, and this is just a flat metric. Here, of course, you still have the freedom to choose an arbitrary time coordinate, which here is called tau, and of course that corresponds to the choice of lapse function. So there's two matter fields in this model, which of course are designed to be possible clocks for you. One of them is this free massless scalar field that you are very used to from quantum cosmology in particular, and the other one is a perfect fluid, which is characterized by an energy density and by an equation of state parameter, okay, which is arbitrary. Now, by doing some proper, clever canonical transformations, you can obtain this kind of simple form of the Hamiltonian, where you have kind of this canonical pair here, V and pi V. So V is a suitable power of the scale factor, so you can think of this as encoding the 3 metric. You've got your massless scalar field, and you have these two variables. So this is a canonical pair which characterizes the perfect fluid. And in particular, this lambda is a conserved momentum, which is the usual conserved quantity you would expect in cosmology for this perfect fluid. And I also rescaled the lapse and redefined this n tilde here to simplify matter. So a very simple Hamiltonian, 3 terms. First comes with the minus sign, of course, for the conformal mode. This is quadratic, this is linear. Okay? So now this is still generally covariant, but there is a particularly simple choice, which is n tilde equal to 1. So, yes?
Where does T appear in the Hamiltonian?
Right, so I'll come to that on the next slide. Hopefully that's clearer. So this is just a canonical pair that comes. So in a sense, this is the variable that is canonically conjugate to this conserved momentum for the perfect fluid.
But it does not appear.
That's right. The Hamiltonian is independent of T, yes. That's right. And likewise, phi doesn't appear in the Hamiltonian because it's just a free massless scalar field and does not have a potential. So the Hamiltonian only depends on pi phi, not on phi, and it only depends on lambda, and not on T, which means that trivially you have two conserved quantities, and which is why these phi and T variables would be particularly natural matter clocks, right? Because they're always monotonic. So in this gauge choice, T is essentially your time variable, right? So you can essentially identify T and tau. So that is, in a sense, a time coordinate that is adapted to this choice of perfect fluid, right? In which dynamics becomes particularly simple, and you can go through this for particular examples. So for -1, which is dark energy, this is a unimodular time coordinate. For 1/3, W equal 1/3, this is conformal time, and so on and so forth, okay? Other people might be familiar with dust models, in which case this is just proper time. So here, perhaps this is a more, so people don't necessarily like perfect fluids very much, right, because they're not really fundamental, but you can derive this in a way that is much more general from unimodular gravity. So you've got this NO Teitelbaum version of unimodular gravity. So in this action, the dynamical fields are your metric. Lambda and T are also treated as dynamical fields, so T mu is a vector density. And if I vary with respect to lambda and T, I get these two equations, right? So this basically fixes the metric determinant in terms of this T field, and this tells me that lambda is a constant. So in this sense, this is kind of equivalent to a unimodular type gravity. And this T mu also induces what you might call a preferred global notion of time. So you can compute the total floor volume between in a region of space-time which has two boundary hypersurfaces, and it will be completely determined by the integral of this T0 variable, which you might therefore treat as a notion of time. Right? This is a time that corresponds to the total floor volume. So in a sense, this is valid much more generally, right? So this was a cosmological model. This is much more general. So I hope that's more convincing. The point is now to look at the classical solutions first. So these variables T and phi evolve monotonically. So they would be very good relational clocks in the usual viewpoint. So I'm starting with T here, and I'm writing the solution, the cosmological solutions as functions of T. And of course, here you see that these solutions have a contracting phase that ends in the Big Crunch and an expanding phase that comes out of the Big Bang, as you would expect, of course. And there are these three kind of qualitatively different cases, but clearly they all have these singularities. Okay? And that's, of course, just what you would expect. The message here is that this is, the form of the classical solutions is now written with respect to one relational clock. But if I change the clock, if I express them in terms of phi time, they look completely different. Right? So you can see here from this plot, phi of T, the scalar field, of course, it diverges at the singularities, as you would expect, right? And if this lambda is positive, so for example, you have a positive cosmological constant or any other perfect fluid present, then as the universe expands, the scalar field will kind of slow down and asymptotically will only go to a constant, right? So this clock kind of becomes very, very, very slow if you see phi now as a clock, and it never goes past a certain constant value. And so now if you write these solutions in terms of phi, of course, they take a very, very different form, right? So here you can see the singularities are no longer visible. They've been pushed out to infinity, right? Because in terms of this scalar field clock, the singularities are at plus minus infinity. But here, the volume diverges suddenly, right? And this is, again, because of what I just said, which is that the scalar field actually slows down with the expansion of the universe. So the singularities are now invisible, but now we have this divergent volume. The explicit form of these solutions highly depends on the clock. Of course, that is not surprising at all from the perspective of classical relativity. But now, of course, when we impose unitarity for these theories, we get completely different answers. And this is already what Lucia focused on yesterday. So we're doing the standard kind of Wheeler-DeWitt quantization, and we do require unitarity, which means that whenever you have a singularity or you have such a divergence in the volume, you have to modify the classical trajectories, right? Because the classical solutions would terminate. If you impose unitarity, that requires a reflecting boundary condition, right? So the state, in a sense, wants to disappear here through the singularity, but because you require the state to be, the norm to be preserved, the state kind of gets reflected And so all these expectation values here remain finite, right? So these are just expectation values. Of course, fluctuations are very large. This was already a question yesterday. Fluctuations in general are large, so here I'm just looking at the expectation values. So this is your standard kind of, if you wish, singularity resolution that you might be familiar with from other models in quantum cosmology. This behavior is much more unusual and certainly hasn't been discussed much in the literature, although there is previous work, of course, which is that sort of classically here the volume diverges, but sort of quantum mechanically these expectation values remain finite, because again you had to impose reflecting boundary conditions, which here at infinity. So this is, if you want, the far future of de Sitter space with a massless scalar field, where the volume, the through volume, of course, of de Sitter space goes to infinity asymptotically, but in terms of these expectation values would actually stay finite, have some upper bound, and then go down again. So in a sense, you would connect this future space like infinity of de Sitter space to kind of a new era, or eon, I guess, as Penrose would call it, in the next universe where you are now contracting. So this is really quite unusual behavior, certainly from the perspective of the usual intuition, which is that we expect funny things at singularities, but certainly not here. Right? So the point I want to make is that these arguments apply to many kinds of situations. So this is some text which kind of summarizes what I already said more or less. So the classical solutions depend very strongly on the type of clock that we use. And so in T time we saw these singularities, the Big Crunch singularities, and in phi time we saw this divergence in the volume. Classically the solutions would terminate. Quantum mechanically we don't allow for that if we say our theory has to be unitary. So therefore the evolution must somehow extend beyond points and become kind of non-singular. And this was already discussed by Gautier and Desmarais in the 80s in a conjecture. Okay. Just to reflect a bit on the choice of quantization method, that's kind of the last technical point I have. So of course here I'm not giving any details, but what we're doing is we're writing down the Wheeler-DeWitt equation in the standard way, and then we're choosing an inner product which in some sense is motivated by the form of the Wheeler-DeWitt equation in the standard way, identifying a metric on mini superspace and this kind of stuff. But of course one might argue that these things all depend on these choices. Okay? So one can take different viewpoints. So here's kind of this more formal viewpoint of group averaging and Dirac quantization, which is very popular. So here you have a constraint operator. You say a physical state is basically obtained from an arbitrary state by acting with this delta of the constraint, which you also put in here to define your inner product. And usually then you also require this constraint operator to be self-adjoint. From that point of view, what we're doing here is basically redefining the constraint operator, right? So in a sense the classical Hamiltonian is given by the lapse times the constraint operator, and in these two theories, in a sense, you would look at different constraint operators where you have made a different lapse choice. And so then, of course, these properties of self-adjointness are also different. I think this point was also made more explicit yesterday. And also you can look at the path integral, and again, if you require unitarity, you will similarly require these different boundary conditions. So it really seems to just come down to this notion of unitarity or self-adjointness rather than any specific details of these quantization procedures. Because I'm in the black holes session, here's a comment that you can certainly generalize these things beyond cosmology, so that's one point I want to make. These arguments are very general. This unimodular formulation in the NO Teitelbaum version always has this preferred global time, if you wish. So you can also define this, for example, for the interior Schwarzschild de Sitter space-time. So this is your standard metric. You can see again this lambda as the integration constant of unimodular gravity. There doesn't seem to be a problem doing that, which then gives me this conjugate time, which is the unimodular time coordinate. I can write the metric in this unimodular time coordinate, and I see that the 3 volume, of course, would go to 0 at finite time. So I would have to impose boundary conditions. Presumably, I would resolve the singularity. So here's the summary. Quantum theories defined with respect to different clocks are clearly inequivalent if we require unitarity with respect to different clocks. And in a sense, what's interesting and also perhaps not appreciated often is that already the classical solutions give you an indication in a sense of where this behavior kicks in. And this is exactly where these solutions terminate when you write them in this particular time variable. And I wanted to focus on this case of the far future of de Sitter, because this is really very low energy physics, right? So in a sense, this has nothing to do with singularities. So the classical arguments we would think should be valid, but still you seem to be forced to have this drastic quantum behavior. Now, you might argue perhaps one of these choices of clock is in fact more fundamental, so unitarity should only apply to a specific class of clocks, perhaps, but then, okay, you have to kind of explain where that comes from. And of course, then, if we're looking at things like claims of singularity resolution on general quantum corrections to classical cosmology, which is the whole point of studying these models, these also then seem to be dependent on these choices. So thank you for your attention.
Thank you very much, Steffen. Also, thank you for keeping the time, which gives us the opportunity to take questions. You're the second.
So, hi, thanks for the talk. You basically started the talk with the statement that unitarity is inherent to quantum mechanics, but for quantum field theory on some, well, let's say on Minkowski spacetime, this also depends on your choice of time slicing, right? So, and in cosmology, I guess there is a preferred notion of time slicing due to the symmetries of the spacetime, but I don't see how in arbitrary setups there would be any globally preferred notion of time that would always slice into Cauchy surfaces, or where you could in any way expect unitary time evolution. Could you comment on this, perhaps?
This is obviously a very different setup, right? So here we're thinking of a quantum theory also of the gravitational degrees of freedom. The statement here I think is even much stronger than what you're saying, because indeed, in the cosmological context, there is a preferred foliation. But even then, just choosing different time coordinates, just in the one non-trivial direction that remains, already gives you these inequivalent theories. So the inequivalence problem seems to be even much worse in that sense. There might be reasons to require unitarity with respect to some choices of time or not, and I'm fine with that, but there's just the point here that you, in general, you do face this inequivalence problem.
Then there's a question by Steve up front.
So I'm a little confused already at the classical level here. Of course it's true that you can always find a time coordinate that pushes singularities off to infinity. Usually we don't do that because that's not the time that's seen by a physical observer, in the sense that if an observer can reach a singularity in finite proper time, who cares whether the coordinate you've chosen says that it's an infinite coordinate time away? So have you looked at what happens just if you stick in a test observer and see whether that observer hits a singularity in finite proper time? Because surely that's relevant to picking out what time you want to be physical.
Yeah, so that's a common argument that often people make, and yeah, that I certainly see the point of that. Here I'm following the philosophy of this relational program, which basically tells you, as far as I understand it, that you can pick a relational clock that has certain properties, and for example be monotonic, not have any turnaround points. And certainly the scalar field clock is very commonly used in models of quantum cosmology, right, as a relational clock. So here making the statement, what is the 3 volume of the universe as a function of this scalar field, this is very commonly used as an observable that people then quantize. And yeah, you might disagree with that, and that's fine. That's part of the discussion. Here I was just kind of following the consequences of what happens if we make that assumption.
I think that's excellent because it gives us something to discuss later on. So yeah, I think we should proceed with the next speaker. Let's all thank Steffen again.